Hello, Narnach here. Welcome back to the human resource machine. So, I was initially going to do the prime factory, but it truly is the last of the bonus exercises. It is tough. So, I'm gonna postpone that one until I actually get a working solution for it. I mean, I've got it like 80-90% solved, but that last bit is what makes it even harder. So I'm gonna spend more time on that and finishing it. So for now I'm gonna work on the sorting floor. And actually this is my second recording of the sorting floor, because the first one, for some reason my game footage actually didn't get recorded. So there's a black screen with me talking, which is not so much fun to watch. So let's re-record this. So the sorting floor. Hey, check out this new office. We've really climbed the corporate ladder together. Thank you. My supervising skills truly are adequate. Your skills are pretty good too. Whatever it is you do over there. So, are you ready? Tell me more. So, how do you sort? Don't ask me. Sometimes I eat the bread before I make my sandwich. Sometimes I put my shoes on before my socks. And I think I'm getting younger. What? I don't think I was ever a kid. Were you? So, we get a list of numbers on the left side, and it's a string. So, number terminated by a 0. And we need to sort them lowest to highest, and then send them out. And we have to repeat that process for every string that will come in from the inbox. And that's it's an interesting thing. It's there are actually very many ways to sort lists of items, but I actually did a little bit of research on Wikipedia. It turns out that a lot of the more efficient sorting algorithms, they require certain data structures to work efficiently, and the solution is going to get very, very complicated. I mean, I've already got 36 instructions, and for the human resource machine, that's already a pretty long program. So I'm actually just sticking with the relatively inefficient sorting algorithm I just worked up here as I was implementing it. And I'll leave more efficient ways to do it as homework for the reader, or I might just record some bonus episodes after I finish the prime factory. So let's get started. So I've already labeled a couple of areas on the floor. We start with the letters, with the number 0, of course, as always. And in addition to that, I'm using 3 variable locations. I'm using a pointer that will point to wherever the list is ending. Then we have an A and a B that we will be using to compare and swap numbers in place. So let's go through the solution step by step and see where we end up. So I'm gonna go through it in the order that we would execute it. So first thing we do is we jump over a section I've labeled output, which deals with actually sending output out to out. Next up, input. So we read value, put it in the pointer. So the pointer starts by pointing to 0, which is this empty location over here. Then we read the number from the inbox, we put it into what the pointer is pointing at. If the number that we just copied is a 0, we are done, because all lists are terminated by a 0, and 0 will never actually be inside of a list. Otherwise, we bump the number of the pointer, so it starts at 0, then we bump it to 1, and then we jump back to the beginning and read the next number, put it down, check if it's 0, and if it's not, we increment it and we keep filling it until we get a 0. So it's gonna eventually terminate, or it's just gonna, oh, if it goes over 19 it wrecks, but we don't get lists longer than that. So after we have copied down the list, we begin with sorting. So once again, pointer we reset to 0, since it ends with pointing at the end of the list. We just yank it back to the beginning. And then once again we jump over an area that I have labeled swap, so we'll get to that later. So we compare. We do that by copying the value that the pointer is pointing at and we put it into A. Then we bump the pointer so it points to the next area. We copy it into B. And after we read each value, we check if it's 0, because if it's a 0, that means we've reached the end of the list and we are done sorting. So this algorithm naturally ends whenever we are at the end of a list, because we don't get to the end of the list until it is completely sorted. So that's a very nice property here. So if we have managed to copy both of the numbers and they're not 0, then we end up holding B in our hands. That's the second number of the pair that we are checking. And we subtract A from it, so that's the first one. And if that result is negative, that means that A was larger than B. So that means that the first number was larger than the last number. So that means it's not sorted. If they are the same, it would be 0, which is not a problem. And if the number would be positive, then A is actually smaller and it's already sorted. So only in case that the number is negative do we actually care about it, and we jump off to an area that I've labeled swap. If that's not the case, then we jump back to the beginning, and because in the process of reading A and B we have already bumped the pointer by 1, we immediately start out by we already start out on the next one. So we can just read, bump the pointer, read the next one, do the compare, and just slowly advance our way through until the very end. But if it turns out that numbers are not in the correct order, then we jump back here. So here, once again, we know that the number that we are pointing at, so let's refer to 0 and 1 as A and B. The pointer is pointing at B, so we know that if we read the value from A, it needs to go into B, because they need to be swapped. So we put A in there. Then we decrement the pointer, so we point to what previously was A and where the value of B should go. So we read B and we copy it because to what the pointer is pointing at, which is where A was previously stored. So then they have been swapped. Okay. So then we check what the pointer is, because we have decremented the pointer by 1. And we check if it's 0, it means we are at the beginning of the list. Good. We cannot go back beyond it. Otherwise, if we are not at 0, but let's say we have 5 numbers here, and we just swap these two, then our pointer is back here. But it could be that the number that was over here that we swap back, maybe it's smaller than the number that came before it. So we need to compare it. So if we are not at the beginning of the list, we bump the pointer down once again, so we can compare these two numbers. And that way we can just yank a number back all the way to the beginning to see if it's until it is finally sorted. And that way any number that we find, we always make sure it is sorted all the way to the lowest position it needs to be. And whenever we start advancing again to the right side, all the numbers on the left side are smaller than what we have sorted so far. So the number of times it needs to go back should be limited, unless like the smallest number is all the way at the end of the list, then it gets yanked back all the way to the beginning. But it will only be done once, and then after that it will advance again. So it's not the most efficient algorithm in the world, but it works, and it's pretty straightforward to explain and to code. So let's see it in action. So our little guy puts the number into 0 pointer. So now we grab the first number, store it in wherever the pointer is pointing at. Boom, done. Next location, we bump the pointer again, so now it's pointing at this empty location, which we store the next value. Boom, bump it again. And then the last one there. And now it's a 0, so we're done. So we go back here. Also interesting property that if you end up with holding a 0, we actually don't need to copy it from here. I just realized. Okay, so we actually just sorted 2 numbers here. I was just focusing on other details. So we've just copied A and B, we compare them. Okay. Next up, 60. So we're now comparing 1 and 2. Well, it's a negative number, so they need to be shuffled. So we do that. We just decrement the pointer again, so we can put the other one in. Okay. So at this point, we don't know if 60 is smaller than 19, so they need to be shuffled again. Well, as a viewer, you can see this list is already sorted. So nothing much is gonna happen, and we will just move on. Okay, so now we are putting that one down. Yes, now the next one we look at here, which is a 0, which is terminating condition for us, so we are done checking. So we're gonna send out the numbers, send out this first one, bump the pointer, read the next one, send it out yet again. And that way is the last one. So that's the first series is now completed. Now we have a 0 that also needs to be sent out. I think it had to. Okay, so apparently not. So this way we can sort it again. So letters basically are sorted by their numerical value, so it used to be sorted as false, so A is the smallest, then the E, then the F, then the L and the S. So this E here is gonna get back sorted all the way over here. And then it gets shuffled and shuffled and shuffled all the way till it's here. Then we do the final compare and we see that it can't get back sorted anymore. And then we just start sorting forward again. And that's a very simple sorting algorithm. And now we get a very long list. So this one has 10 elements, so that means if you have a very complex sorting algorithm or a very inefficient one, this is going to take a very long time. Which in this case is actually the case. Especially a number like this, it needs to be back sorted quite a bit before we can advance again. And we're basically moving one item at a time until it is at that point in time most correct position. And we're just sending things back in time. So this is something that I believe this resembles a bubble sort of sorts. It's not efficient, but it's pretty straightforward to implement. And in this case, human resource machine, it's really hard to keep track of what's going on with the code because it's just a very long list and lots of jumps, and it's really hard to see where things are going, even though you can label sections. So sticking with simple for a first implementation definitely works to help you just understand what the actual problem is, and then you can just optimize it later. I believe people have actually managed to implement a quick sort in this. That was must be quite an interesting challenge, because a quick sort, again, from what I read about it, you subdivide the list in many sections, but it's pretty tricky to work with that. And the last is a one element item, just to double check that you don't choke on that. And in here we have 1158 instructions on the speed challenge, which isn't quite fast enough. Speed challenge is 700, but it works. So one of the things that I was musing about at the end of my previous recording, but since we have a little bit of time, might as well just get into it. One of the things is that as you sort, you build up some knowledge. One of the things you know is that after you have checked A and B the first time, so you copied the first two elements of the list to A and B and you've ensured they are not 0, then you know about those numbers that they are not a 0. So you could actually have a second version of this copy loop or this check loop without the 0 checks. That might make it slightly faster, because you skip 2 instructions for every run through, especially if you are just checking things. It might be slightly faster. On the other hand, you would need to be jumping back and forth through things quite a bit. So that is something. Yeah, that's something you could do after you have swapped, because then you know the number is correct. So in this case, I specifically implement the swap before the main code, so I can jump to it and afterwards fall through back into the compare loop, because that saves 1 jump. And since you need to jump here anyway, that's actually slightly more efficient. It saves 1 instruction, and it's during runtime it also saves 1 instruction for every iteration. But the thing is, if after this we basically inline a copy of the compare code before we move on without the checks, that might even be more efficient. And we don't even need to put it behind it, we can actually just inline it here. So let's be slightly adventurous and code it in here. So let's start with it. So in here we have a copy from whatever the pointer is pointing at. That's this one. Then we don't need to do a jump if 0, because we know it's not 0, because we just copied it. We just swapped them around. So then we also need to store it in A. So we copy from pointer, put it into A. We bump the pointer, we do that. Then once again we copy from the pointer, because we need to read the next one. We copy it to B. Yes, then we subtract A. So that's what we do, and then if it's a negative we jump out, and otherwise we jump back. So in this case we don't jump, we just fall through. So all we need to do is add a jump to negative, and we do that back to the swapping code. And here we can actually have the jump if 0. So if it's a negative, we go back, which we can just add in here. That's there. Yes, like so. So this is now, we use more instructions because we duplicated some code, but it's more efficient because we skip 2 checks to see if numbers are 0 on codes that we know the numbers are not 0. So this might end up being reasonably faster for the longer lists where there's a lot of shuffling about of numbers. Because as long as we stay up here, we are good. Okay, now we get the long list. See how this goes. So as long as we stay in here, we're good. I wonder how much this is going to save. we have the last 4 that still need to be sorted through. So what I do backpedaling whenever I encounter a number to basically carry it back to the beginning. It's a divergence from bubble sort that I later discovered. Bubble sort basically just goes through from beginning to end, and once it's done in the end, if it has changed anything, it just goes back and just sorts again. So in the worst case, if you have a list that is perfectly sorted with the exception of the lowest number being all the way at the end, it will move the last number back by 1 step every iteration. So a list of 10 items would need, what is it, 10 minus 1, so 9 steps to get it back to the beginning, which seems like a bit much, and in my case it would actually just go through in 1 step, so it's a bit like cocktail sort in that regard. But as I said, this is it's a first implementation I just got when I started working on this, and it worked okay enough. So 1088, so that's 70 steps faster. It's not a lot, but it's a little bit. But we use more instructions, so I think there's a lot of room for optimization in this one. It's definitely fun. And it's probably going to be interesting to see how some of the sorting algorithms that actually work with lists and splitting them into multiple lists, how you're going to carry that out if you actually have no very limited amount of space and no support for actually list manipulation and functions and things like that, because you're really low level here. So that's I think it's an interesting challenge. So with that, let's call this sorting floor. For now, we have a working solution. It's not optimized, but it's working. So let's have a look at the end program. Congratulations.
Congratulations. You've really become an invaluable instruction follower.
Yes, don't worry. Your job is safe. We've replaced you with this electric box.
It's called a computer. It iterates through a list of simple instructions called a program.
It has a small amount of memory to store data while processing, like tiles on the floor.
It has inputs.
And outputs.
Its simple instructions can be used to get around infinite combinations to compute just about anything you can imagine.
A truly efficient worker that never sleeps.
It's going to change everything.
Please take your pennies and enjoy whatever it is you people do out there. Congratulations.
So, congratulations. We've built a computer. We've been replaced with a computer. So, bye bye. We descend the elevator one last time. And that's it. So, as I was saying before, there's still a couple of videos that I want to make. I want to solve the prime factor, and I'd like to do optimized versions of the puzzles I haven't managed to optimize yet, just to complete the series. And they will come at some point. For now, I'm happy that I managed to make it all the way to the end. So I thank you very much for watching. And if you haven't done so already, I have a series on another game called TIS 100. That's also a programming game, but while the Human Resource Machine is very playful and very nice in a graphic sense kind of way, TIS 100 is a lot more raw. It's actual assembly programming. The options, the instructions you have, they offer more options, and you have more things you can do in parallel, because you're actually just writing code to make multiple programming cores work at the same time. And the puzzles you get there, they get very interesting as well. So If you want to see more and don't want to wait for more videos in this series, I highly recommend that you check out TS 100. And with that, I thank you very much for watching and hope to see you again next time. Bye bye.